started. I'm Ryan. I'm the other instructor for the optimization class. I'm going to just give a few slides here. Mainly, I want to show an example. And in this example, we're going to see a problem that we'll kind of revisit throughout the semester. And then I'll hand it back over to Jeff, and he's going to start with our course material. It's just kind of leftover stuff from the introductory lecture. Okay, so Jeff already said this in a couple ways. I guess I'll say it a little bit differently. So in many different machine learning or statistics courses, also other types of courses like engineering courses, you learn how to turn like a question or an idea, either that you have or somebody else has, and it comes to you for help, into a problem, a mathematical problem. And in particular, you learn how to oftentimes turn it into a minimization problem. So you take this question and you turn it into something like min f. And part of that is choosing what f is, right? That's the main thing. How do I choose a function so when I minimize it, it captures this question that I have? That's what you learn in some other courses. In this course, you're going to learn that this minimization here, that's not the end of the story. In most other classes, you learn about, I transformed this concept into a problem, here's the solution, and you see some plots of how it's computed, but you don't actually learn what happens after you write that down. So we're going to learn that's not really the end of the story. The composer goes on after that. We're going to learn a few things. The first thing, which maybe is kind of obvious, is that we're going to learn some algorithms for how to solve this problem, minimize f of x. And when there's more than one algorithm, and oftentimes we'll have many algorithms that can be applied to a particular problem, we're going to learn how to choose between them, depending on what we're looking for, maybe what's special about the problem, what's special about our computing resources, that kind of stuff. We're also going to learn, and this is maybe not so obvious before you go optimization, we're going to learn how knowledge of algorithms for this problem, they actually influence the translation. So if I know a lot about how to solve min of f of x for different types of f that relate to my problem, I might actually think that one of those translations is the best. So it can work backwards, and we'll see examples of that. And this one's also not obvious. I was actually very surprised when I saw examples of this for the first time. We're going to learn how knowledge of algorithms for computing a solution, they can actually help you understand things about the problem, or even prove things about the problem. Sometimes an algorithm can be used to prove things. If you want to know something about the properties of the problem, you can actually kind of step through the algorithm as you prove. As a thought experiment, not actually as a computing experiment, but as a thought experiment, and you can prove something about the problem you didn't know before. So those are just some things about how this course fits in. We kind of covered this in the last lecture, so I'm not really going to go into detail about this, but I just wanted to maybe point out a couple of problems that were mentioned last time that are optimization problems, that are statistics problems that cannot be task optimization problems. So we had a lot of examples last time of statistics and machine learning problems that were optimization problems and also that weren't. I just want to point out a couple more. So particularly in clustering, a lot of clustering techniques themselves are actually algorithms. They're not criterions that we write down to minimize. For those of you who are familiar with hierarchical clustering and statistics, hierarchical clustering, you basically just choose what's called a linkage function. And that's a function that tells you how dissimilar two groups are from each other. There are lots of choices for that. Once you choose that linkage, you just run through a procedure. And that procedure is described as follows, basically. If you're doing bottom-up hierarchical clustering, every point is one cluster, and then I just join the two closest points, make them into one group, and then I repeat. And that's what gives me a sequence of clustering time. That's just an algorithm, it's not a criterion. It's actually, for that reason, it's very hard to study hierarchical clustering and prove things about how stable it is under predictions of the data, or other things, because it's really just an algorithm. Another example of something that's an algorithm is probably one of the most natural tools that people use in statistics and machine learning. It's cross-validation. So let's suppose that I have some training model, and I want an estimate of its prediction error. I want to know if I could draw points out of sample, take the same distribution as what I observed in the second sample, what's its prediction error going to be? Well, the cross-validation estimate for prediction error, that's not given by minimizing some objective function. Right? I'm not saying that the estimated prediction error is equal to the minimum of some objective function like a likelihood or a p-line likelihood or something. That's just given by a procedure that's called cross-validation, where you split up the data into, say, 10 parts, 9 parts, we train the model, we test on the part left out, and we repeat. And that's very natural. There's nothing wrong with the procedure at all. Again, actually, very little is known kind of theoretically about cross-validation. It's notoriously hard to study. And I just gave you 2 examples of things that were not optimization problems that were in statistics and machine learning. That doesn't mean that they're bad or there's anything wrong with them. It doesn't mean you should avoid that kind of study in general. I'm just trying to suggest that if you can catch something as an optimization problem, if you have that flexibility, oftentimes it's really helpful to do so. And we're going to see lots of specific examples as we go through the quarter of why that is. I'm sorry, it's a quarter. I'm still thinking around the quarter system, the semester system. Okay, so I have this one slide I wanted to talk about. Actually, when this course was last offered, Jeff taught the course with Carlos freshman. And Carlos had a slide that said, how did Carlos get a job at CMU? So I wanted to kind of play along that theme, but go even earlier, how did I even get a PhD? I can put this online because I don't want this to be on the record of how easy my PhD thesis was. But just keep it between you and I, and we'll have to edit the video and we can edit this part out. So how did I get a PhD thesis? This is really what it came down to. And after you take this course, I'm pretty sure all of you read my PhD thesis and understand the vast majority of it. Because it's really all these following steps. The first step was just recognize linearity. That sounds super easy. Recognize that something that you're looking at is a linear transformation. And then we'll learn probably, not this lecture, but the next, that there are a lot of rules for linearity and convexity, so immediately I saw that it was convex. So I have a convex problem. That was the first step. The second step was derive the dual. So we're going to learn how to do that with lots of examples. The dual is basically an equivalent problem that sometimes is easier to study. So step 2, I derive the dual. Step 3, I looked at the KPT conditions. These are optimality conditions that describe when a particular point is optimal or is a solution. And it's basically the extension of take the gradient set it equal to 0. A little more complicated in case you have constraints and non-differentiable functions. Okay, so that was step 3. And at that point, I don't think people were super convinced that counted as a PhD thesis, so I made a movie. I think that really sold everyone. So here's the movie I made. And basically, with these 3 steps, and with the power of convex programming in this case, I could compute the solution path of a particular problem. And it looks like that. So that's not supposed to make a lot of sense, that movie, but maybe as we get down the line in the semester, we're going to cover something called path algorithms. And then after that point, you'll know everything in my thesis. So. Okay, and here's the example I wanted to give. I wanted to talk about, because we're going to see kind of this type of thinking throughout this semester. So let's suppose we're in the sparse linear regression setup. So what does that mean? It means we have some vector y of response segments, and we have predictive variables, and I'm going to put them into a matrix. So the columns of this matrix, call them A1 through AP, those are my predictive variables. Right? Standard linear model. I just want to write y approximately as a linear combination of my predictive variables. So y is approximately equal to a times x for some vector x. But in this case, let's suppose the number of measurements I have, n, that's a lot less than the number of predictors, p. And I can think of these variables, a1 through ap, as maybe a lot of them could be unimportant. Maybe I have so many predictors that I measured just because it was easy to get all of them. I didn't really try to think too carefully about which ones were important. And now I want to fit this model, but a lot of those predictors are not important, probably. So what I want to do is I actually want to constrain a lot of the entries of x to 0. picture of that. This might be y. So y is, I have 5 measurements here, not very many. And I want to write it approximately as a linear combination of these predictors. So each column in that matrix is a predictor times x. And x should have very few non-zero entries. So the ones that are white here are 0, and the ones that are dark are non-zero. So I want to adaptively select elements of x to be non-zero. That's the problem. So what's an example of that? Let's suppose that y was maybe the size of a tumor, like some particular type of cancer, like prostate cancer or something. And I believe that that's approximately a linear combination of some genes that we measure, but I don't know which genes. And I measured a lot of them. Suppose I measured 20,000 genes. And they're not all important. Right? It's not hard to believe that not all genetic information is relevant to the size of some of these tumors, say, prostate. Some of them are, but I don't know which ones. So that's the problem. Sparse linear regression. So, okay, if I just did regression, if I just minimize the usual regression criterion, that's like the square error between y and x, that would work. It would work for a couple of reasons. The first reason is that now we're going to dense x. I won't necessarily get an x that has zeros in it. And the other reason, which is probably equally important, is it's not well defined as p here. So this problem is convex, but it's not strictly convex. It has many solutions. In fact, it has infinitely many solutions. And the problem is that if you give me any variable, say variable number 20, I can always find a solution such that 20 is not in y. That's true for any variable. So it's not really interpreted. It's not well defined. So here's an example of, we have a task that we want to do. We want to basically approximately fit y to ax with many entries to x being 0. And now we want to think about how to do that in terms of an optimization problem. So I'm going to talk about 3 methods that exist in the literature that are quite popular. Each of them are pretty well known, so you've probably heard of them. But they end up having pretty different outcomes in terms of the way that people look at them now and the way that people actively use them. So the first is best subset selection. This is an optimization problem, so it's of the form minimize some function, but that function is not convex. The second is what's called forced stepwise regression. That's just an algorithm. It's not minimizing any particular criterion. And the last is called Lasso regression. That's also an optimization problem like best subset selection, but it's convex. That's the difference. So what's a subset selection? It's a very natural idea. We just say that we want to minimize that regression error, or least squares term, subject to, I'm going to say, I want at most k entries to x be non-zero. So I specify k ahead of time. So let's just suppose from the genetic example, I think k equals 50. Well, I want 50 out of 2,000 or 20,000 predictors at most to be non-zero in my linear model. And this notation here, the x with the 0 norm around it, that just counts the number of non-zero components. So it's not convex, and I'm calling it a norm in parentheses because it's not really a norm either. It's missing one property of a norm. We'll find that out when Jeff covers norms, I think, on next Tuesday. So here's an example of what the level sets look like, or the sub-level sets look like for this L0 norm. If we're in R2 and I look at all the points such that the 0 norm is less than equal to 1, that's just all the points such that either x1 is non-zero or x2 is non-zero, but not both. That's it. So here's the sub-level set of the 0 norm. It's a cross, right, and extends infinitely on both axes. And now, you probably don't learn the definition of convexity, but if you remember what it looks like in the picture, that's not convex at all. That sub-level set is not convex. So what do we know about this problem? The problem is actually NP hard. And the best algorithms for this problem are really just brute force. Can't do much better than, well, let's look at every subset of size k, regress y on that subset, and choose one that has the smallest least squares there. In practice, the solution can't be computed for p larger than about 40. So if the number of variables is larger than approximately 40. We don't know what the solution is. And another thing is that very little is known about the properties of the solution. People don't know in general a lot about various statistical properties of the best subset selection. So here's another natural idea called forward stepwise regression. We basically start with a guess of our solution to be 0, so all zeros, and then we're going to repeat these steps. We're just going to follow this recipe. We're going to find the variable j such that the inner product of the jth variable with y is larger than absolute value. So if I think about all the variables or all the particular variables as having mean 0 and sample variance 1, then that's choosing the variable that has the highest absolute correlation with the response. Right, so I want to pick the variable that's the most correlated with the response. That makes sense. It seems like it's probably the best variable to pick. So we pick that, and then we throw it in the model. That means that we regress y on that variable. Okay, so now that's in the model, it's going to be in the model forever, for the rest of the algorithm. Next, we're going to find another variable, a different one, that's most correlated with actually the residual from regressing y onto that first variable. So what's left? What hasn't been explained yet? That's the residual. That's y minus aj times xj. That's what we haven't explained yet. And y. Let's find the variable that's most correlated with that residual. And then again, we throw that in the model. And now we do a bivariate regression. Two variables, regress y and those two variables. And then we repeat. We find the third variable that's most correlated with the residual. We throw it in. We regress onto those three variables, etc. And we're going to stop at some point. So again, we pick a stopping point. We might pick when we've thrown in like 20 variables in the model. So this is an algorithm. It's not minimizing a particular criterion. The x to be out of it, it's not equal to the minimum of some particular function. People actually try really hard to find what function is not minimizing, or a continuous version of this forward stepwise procedure is minimizing. That's been an active topic of research. But we don't know it yet. We don't know if it's minimizing a criterion. Some properties of this estimate are known, but not many. And the proofs of those properties are actually relatively complicated. So some pretty heavy-duty math is required to prove things about this estimate. For example, you might ask, let's suppose that y was really equal to a linear combination of a small number of variables plus some noise. And that noise had a particular distribution. You could ask, how large does NP have to be that if I do this forward stepwise procedure, I get an estimate of x that's so close to the truth. So that's an example of a property you might want to know. What's its convergence, right? How close is it converge to the truth? Or how fast is it converge to the truth? The proofs that it has a good convergence that are actually pretty complicated. So here's the last one I'm going to talk about. And this problem is called Lasso regression. It's an acronym. It stands for, see if I can remember this, least absolute shrinkage and selection operator. So basically, what happens when we take the best subset selection problem, and all we do is we replace that 0 with a 1. So again, we minimize the least squares term, but now it's subject to the one norm of x being smaller than or equal to some pre-specified constant t. And the one norm is the sum of the absolute values of x. And it's a convex norm. So in a sense, or actually in a pretty specific sense, this is a convex realization of the best subset selection problem. So it's the convex problem that's closest to the best subset problem among all the problems that we could choose that are convex. So what do the sublevel sets of the one norm look like? And by just add together the absolute magnitude of the components. So here's what the sublevel set looks like in R2. If I look at all the points that have one norm smaller than or equal to 1 in R2, it looks like this diamond. Right? Because if I take any point outside this diamond, then when I add together the absolute value of x1 and absolute value of x2, it'll be equal. So again, you might not remember the definition of convexity, but that should look at least more manageable than that cross. And that's a nicer step. So this is convex. What are some properties? It delivers exact scales in solution. So That might not be obvious. It's not as obvious or as natural as when we write on this problem that it actually gets us what we want. If we wanted an x that was sparse, it should be, at least it was not obvious to me when I saw this problem the first time, that that's the property of the solution. But it does, and the lower it makes t, the more zeros we get. This problem is convex and it's readily solved, so there are lots of algorithms to solve it. And many properties are known about the solution. The proof of consistency, the property that I mentioned for stepwise regression, where we can say that with a certain amount of data and a certain model for the truth, our estimate is close to the truth. The basic proof of consistency for Lasso is like 5 lines. It's very, very short. And it uses basically a property of convexity and then a property of the errors, so a little bit of probability. So those two things, we basically have consistency. So here's a quick comparison. I did a Google Scholar search for best subset selection, for stepwise regression, and for Lasso. And I looked up how many hits there were on Google Scholar. So Lasso is kind of like a generic term. I don't know if people say that in other fields. So I made sure I searched for Lasso and statistics together. I don't know if there's like a cowboy journal research or something that would pick that up. But, okay, so searching with Lasso and statistics together, it's already pretty quick here. I got 13,000 hits. So 13,000 hits in Google Scholar. For stepwise regression, I actually searched for that and all its alternate names too. So it's known as different things in different fields. It's known as orthogonal matching pursuit, sometimes in signal processing. People also call it forward variable regression. So combining all those different names, which I think some of them overlap too, came up with about 7,000 hits. And best subset selection, again, searching under all these different names, had about 2,000 hits. So this is not to say that the Lasso is the answer, and it's way better than either of those problems, but maybe this is to say that it's a lot easier to actually work with Lasso than other problems. And that's why a lot of people write papers on it, because it's a lot easier to prove things about it, to come up with algorithms for it, to work with it, to apply it, because of the fact that it's a convex optimization problem. It's a lot more amenable to research. How many algorithms do you know for each problem? Well, for best subset selection, I mentioned there's really only one, that's brute force. So if you're not happy with that, it's too bad. Either that or you should maybe prove that t is equal to np and then you get a Turing award or something. So best subset selection probably the least of your concerns at that point. For stepwise regression, there's one algorithm, and that's itself. It is an algorithm, right? We don't know another way to predict the solution. In the last one, there's at least 10 algorithms. And there's probably more like 20. There's a ton of algorithms that are published all the time. Even today, there's just continually algorithms being published for the Lasso in different situations. In situations where I have maybe distributed computing, or I have a huge number of coefficients and a tiny number of non-zero, or where I have roughly balanced n and p, or where I want the entire path, not just the solution for one particular value of that parameter t that controls the balance. There just are tons of algorithms for that. And lastly, what about the properties of these problems? Like I said, very little is known about best subset selection. Some things known about forward stepwise regression, but people are kind of struggling in some sense. I don't want to get in trouble because I don't know this literature quite as well, but I get the impression that it's a lot harder to make progress in that. And the Lasso, there's just tons of things to know about. Okay, and we're going to revisit this idea of placing either a one norm constraint or a one norm penalty throughout the semester, because we're going to see that this is kind of trendy, it's true, it's popular, but it's also useful. So we're going to see we can induce what's called sparsity in a lot of different aspects, not just in a linear model, but in a bunch of different statistical models as well. Okay, yeah. How do we choose T? That's a great question. I think we'll probably get to talking about it in a little more detail at some point, but it depends on what your goal is. If your goal is just prediction error. If all I want is an x that actually, such that ax is very close to y, then a good way to choose t is actually cross-validation like you mentioned. I could split up the data into a bunch of different parts. I could train a Lasso model on a bunch of the parts with varying values of t, and then I pick the one that gives me the best pair on the held out data. If I actually care about recovering a good model, like an interpretable model with few coefficients, or one that actually approximates the truth, that's a little bit different goal than prediction error. It might not seem obvious, but sometimes a model that predicts best is not necessarily the model that's easiest to understand from a scientific point of view. So if that's your goal, then it's a little bit harder, and maybe it's a little bit longer story. Yeah. Sorry, I can't hear you. Creating zero. Good question.
What's the question?
The question was, what's the intuition behind creating zeros? Why does the Lasso give zeros? Let's see if this works. I can actually. Can everyone see that? Not very focused.
Oh, there you go. Autofocus.
Autofocus. Okay. Okay, so let's just stick with this picture. The intuition actually is as follows. So this is the region that we constrain the variable psi, and it looks like a diamond, right? So let's just think about two variables, a diamond and R2. And let's suppose that that was the actual least squares solution. So if I didn't have any constraint, this would be the solution. And now I'm going to draw contours of this function. That's a quadratic function. Let's suppose I draw its contours. They have some kind of elliptical shape, right? And the Lasso solution is the x that minimizes this subject to having one norm less than or equal to, say, 1. So it's the x that minimizes this function subject to lying in this region. Another way of putting it is that it's the first time that one of these contours hits that diamond. So in this case, you can imagine that it hit the diamond right at a point where x1 was equal to 0. So in this solution looks like 0, x2. Now you could say to me, well, you just drew that to hit the corner. That's not a proof. That doesn't work. And it's true, it's not a proof. But in higher dimensions, if I draw a diamond, which I can't, but if you think about a diamond in, say, 20,000 dimensions, it actually has a lot of corners. There are a lot of points for which some components are actually 0, and it's a lot easier to hit one of these corners in high dimensions than it is to hit a face, where everything is non-zero. So again, that's still not a proof. How do we know that the Lasso actually gives us zeros every time we run it? Why can't I run it tomorrow and it gives me why is it true that for some value of t it's going to give us some coefficients equal to 0? That's going to come from studying the KKT conditions. So when we learn those, probably one of the examples we'll learn is how to prove that it's never going to fail us. We're actually going to get this. Good question. Any other questions? Is there a question? Okay.
All right, so let's get back started again. So, yeah. The other thing, so I had a little bit of an intuition for the Lasso question as well. If you sort of imagine, so all right, I'm going to do this the old-fashioned way, right? So you imagine your diamond here that is the L1 constraint. So you take these lines and you extend them out to infinity, and you take these lines and you extend them out to infinity, right? If you imagine zooming way out, you have like a big X, right? And if you imagine that the contours are approximately circular for the objective function, for the squared error objective function, then what you're going to do is you're going to get the point within the diamond that's closest to the least squares solution, right? And if you fall between the arms of the x, that'll be at a corner. And if you fall within one of these arms of the x, right, between the two parallel lines that are being extended, you'll get a side, right? And there's just a lot more area that's between the arms of the x than is within the arms of the x. So that's sort of the intuition that I have for why Lasso works. And again, totally not a proof. We may see proofs later, but I wanted to give you that one as well. All right, so we have a little bit of administrivia. We've posted the schedule of homeworks and other work up on the website. It's either posted now or it'll be up soon. A couple of highlights that people probably care about. The poster session is going to be Wednesday, December 12th at 3:30 in the Newell Simon atrium. Okay, so put that on your calendars. The midterm is going to be Tuesday, November 6th, which that'll just be in class. Homework 1, that's the most immediate of all of these, is going to be released on hopefully next Tuesday. We may not quite make that deadline. We'll see. Aditya sent a very nice email to the class group about how to do scribing, but I just wanted to briefly reinforce some of the points he made. So first of all, when you're signing up, put your first name and a way to contact you. So your Andrew ID is a good way to contact you. We don't just want to know who you are. We want to be able to track you down if you don't show up for class that day. And also your co-scribes want to be able to get in touch with you. So name plus a way to get in contact with you. If you somehow mess up the Google document, let us know so that we can fix it. We don't lose any data if possible. Somebody did briefly mess up the document, so if you signed up a while ago, it might be worth checking and make sure that you're still signed up. We want to get everybody signed up as soon as possible so that we don't wind up with a situation where some lecture doesn't get scribed accidentally, because we'll probably discover that when everybody's studying for the midterm, and everybody will be very sad to have a missing lecture. Right, and how to do scribing. So the basic idea is that after the lecture, you and your co-scribes get together, divvy up the work however you want it. You make a document. You send it first to Aditya, who is the master of scribes, and yeah, he took the job because we gave him that title. So he'll review it. He'll maybe send you some comments, maybe do a round of comments. Then the professor who did the lecturing will review it to make sure that it moderately accurately describes what we thought we were saying. And then it gets posted on the website. So the goal for scribed notes is basically to be as complete a resource as possible for understanding the lecture. Include, if we did a proof of a theorem, include at least a sketch of that proof, whatever details you can get into the notes. The idea is to make it so that you don't have to go and always rewatch the video if you don't understand something from the slides. Right? So the idea, again, think about what it is that you would want if somebody else were scribing the lecture for you, and try and put that in the document. We're hoping that this is not going to be much work for people. It's once in the semester. It's shared among a bunch of people, and we're hoping it becomes a great resource for everybody. So if anything interrupts that idea, let us know. We want to fix it. Yeah. The plan is that. It'll depend on how good I get at doing the appropriate post-processing. I imagine the first few lectures may have a little bit longer delay because I'm still learning how to use all the software. But yeah, we'll try and do that. All right, any questions about scribing? Yeah. There's no specific due date, but your other classmates will start tracking you down Um, we suggest maybe 10 days after the lecture for the initial draft write-up, and then we'll try and turn that around as quickly as possible to get it up on the site. All right. Any questions about scribing or about the class schedule? All right. So let's get to something more fun then. Assuming that, there we go. All right. So I wanted to give an example of, so Ryan just gave an example of how you go from a problem, regression when you believe some of the covariates are not relevant, to an algorithm. He gave 3 different ways to do it, which is the usual situation, that there's at least 3 ways to do any particular problem. I wanted to go and give a different example because it illustrates a few different points. So imagine that you build yourself a new robot, you slap a camera on top of it, you drive around, you take a photo from the camera, and here's the photo that you get. All right? So you want to understand what it is that you're looking at. Right? So this is the image understanding problem. You want to get some computational representation of what's out there in the world based on what it is that, the pixels that come in from your camera. All right? So let's take a poll. How might you guys try and set up that problem? Think about it for a few secs. I'm sure you guys have seen papers that try and solve the problem, at least some of you. Yeah? Okay, so you're thinking then of computer vision as inverse computer graphics, essentially, right? You have some mapping from what you believe the scene looks like to what you think the image should look like, and then it's an optimization problem to figure out the best scene that explains this particular image. And what sort of representation are you thinking about for a scene?
Well, it could be an image that's like the most critical representation. So I have
Okay.
like I have.
Okay. Right. So let me repeat that so it gets on the microphone. So the idea there is that you have images of objects in the world, and you imagine that your model is just, you're seeing one of these things, and you want the one that's closest. This is called sometimes the pop-up model or the cardboard cutout model. You imagine that the world has, somebody's holding up a placard in front of you with the image that it is that you want on top of it.
Yeah, or it could be some generation procedure like set of transformations
Mm-hmm.
and set of and then like some vectors applied and
Okay.
objects.
So what you're saying there is basically like the standard 3D scene model that you imagine is going on inside every computer game that we've all played, right? Where you have some, 3D coordinates and orientation of these solid bodies that have textures mapped on top of them, and then you have your generation model as you throw it through your latest, Radeon or whatever, and it comes out up on your screen, right? Okay, so yeah. Those are 2 very, very different models, right? You could imagine that they have very, very different optimization properties, right? Any other suggestions for what the model might look like? Yeah. Image segmentation. Right. Right, okay, so your model there, it's not 3D at all. It's a 2D model where you assign to each pixel of the image some sort of information like, at the minimum, a segment ID, and then maybe like a description of the object that it came from, right? Okay, so that's even a very different model, right? So we've had like a 2D model, this sort of image segmentation model, or a 3D model, which is the, throw it through your graphics card model, or a 2.5D model, which is this, the pop-up model, right? Any other suggestions? Those were the three that I came up with when I was thinking about it last night, so I'm glad you guys came up with them. I would have given any ones that you didn't. So let's suppose then that we're going to fix on this 2D segmentation model, right? So our optimization problem is going to be to try and find the different segments of the image and attach identifying information to the segments. So now we have to turn that into an optimization problem, right? That means we have to select variables, constraints, an objective function. Any idea what the variables should be of our optimization problem for this for the segmentation model? Okay, so there's one variable per pixel, and that variable is an integer from 1 to, say, 10 if you believe there are 10 segments. Okay? That's a good set of variables. Any other sets of variables? I'm sorry? So you're thinking of... oh, I see. So for each segment, you want not just the idea of the segment, but this is a face, or this is a barn, or this is a cow, or something like that. Yes, right. Right, so you could have those in addition to those variables, right? Yeah. Mm-hmm. Mm-hmm. Right, right. So you would have a parameterized class of this is not just a cow, but it's one of those black and white cows as opposed to one of those brownish cows, right? Or this is a barn and it's a red barn as opposed to a green barn, right? Yeah, so that's good. And you could have color, texture, SIF descriptors, whatever it is that you want to describe your segments. Any other thoughts about ways to set it up? Yeah. Yep. Very good. So you could have the variables not on the pixels themselves, but on the edges between pixels, and you could try and identify what the edges of the segments are as your variables, right? And you could have a combination of those two. You could represent both the pixels, what class they were, and also the edges, whether there was an edge between any pair of pixels or not. All right. Cool. So you guys have now gotten all of the ones I thought about, plus some more. Now we have the variables. How are we going to set up the constraints or the objective, right? So there's not necessarily much difference between constraints and objective in this case, because you can have sort of soft constraints, which you think of as terms in the objective, right? You pay for violating them. So how would you set those up? Like, what would a typical constraint be? Yeah. Nearby pixels have a similar value. Yes, right. So, so are you thinking something like this graph, which I've seen in a ton of papers? Right. We have a grid of pixels like this, right? And they're connected like this, right? And then you have a variable associated with each of these little circles. Obviously, I can't count, so there we go. And yeah, so something like that, right? That's the sort of thing you're imagining? Cool. Any other thoughts about how you might set up the constraints? Yeah. A single, yeah, okay, so that's another constraint, right? So that might not actually even be a constraint, right? So if you have, I mean, you can think of it as, xi is in, 1, 2, up to 10, right? So often people take those simple constraints and they pull them out and they call them just the domain of the variable, but you're right, that is a constraint, right? And especially if you represented it, right, you could represent it as xi being an integer from 1 to 10, or you could represent it as 10 binary variables, one of which was turned on, in which case you'd have positive and sum to 1 constraints. Any other thoughts? Smoothness of the segmentation, right? I think these edges do enforce some kind of smoothness on the segmentation, right? You want neighboring pixels to have similar labels. So are you thinking of that, or are you thinking of some other kind of smoothness as well? You're thinking of this, okay. So we would write it, often it would be something like, you would pay a term, your objective would have in it sum over, I, j in your set of edges, the distance between xi and xj, where the distance could be something as simple as 0 if they're the same and 1 if they're different, or it could be something like, it's better to mistake a cow for a sheep than it is to mistake a cow for a barn, right, or a cow for the Mona Lisa. All right. Any other thoughts about this? Yeah. Minimum. Oh, I see. So if you're different, you should have different descriptors. Yes. Yeah, I like that. So nature doesn't conspire against you by taking two really similar-looking objects and putting them abutting each other with an invisible line in between them. That's actually, perhaps like a magic show would do that to try and confuse you, but yeah, it's probably a very good constraint. So I was thinking of one more, which is that this grid graph is actually, why use it, right? You could include longer edges like that, right? And have different weights on them, right? You could say that, two things. The strength of an edge depends on how long it is, how far apart the two pixels are, but you want yourself to be similar to the second guy from you, right? And that'll be a slightly different way of setting up the constraint. It'll have more or less the same overall effect, but it'll change the setup of the optimization problem and maybe change the algorithms you can use. You could also imagine, for example, you could run an edge filter over your image, right? And if you do that, you could say that graph edges that cross a strong image edge are much weaker than graph edges that don't cross a strong image edge, right? So I expect to find object boundaries at obvious edge detections in the image. Right. So if you have, so I'm going to sort of magnify a single pixel here, right? So you have like all of these sort of short edges and longer edges and really long edges, right? And there are a lot of these things. You could imagine that having all of them there would be sort of the best representation of the problem, because it would make it would include sort of the richest representation of pixel similarity, of pixel nearness in the image. But you could also imagine that was expensive, so maybe you can subsample some of these at random. And maybe subsampling at random isn't going to mess things up too much, right? You could have, there's a ton of different local features that you could use. We already mentioned a bunch of them. A ton of different edge detectors you could use. You could try and, so I wrote these potentials d of xi, xj down. You could design them by hand, think really hard and say, yes, this is the right way it should be. Or you could try and learn them from data, right? And then the learning problem is itself another optimization problem. And depending on how you set up the feedback in the learning problem, it's going to be a very different optimization problem, right? You could imagine that you have fully labeled images as your training data. You could imagine you have some unlabeled images. Often it's much easier to get unlabeled images than fully labeled ones. You could imagine you had partially labeled images, so somebody went and scribbled, here's some foreground, here's some background on each of your images, right? So that's gonna all be different. And one more constraint that nobody mentioned that I think is possibly important is a balancing requirement. So if you you could put into your optimization problem that you don't want your individual segments to be too tiny or too huge, right? Because a lot of times if you set things up so that you're just trying to find, let's say, two different segments, well, the best way to cut the image is the bottom left pixel is kind of different from the ones around it. So there's one of your object and the rest of the image is the other, right? And that is not really what we mean by the optimization problem usually. And so putting in some kind of a balancing problem, which would it would look something like you know, the number of times the number of let's write it this way: the size of the set the size of the set I such that xi equals 3, right? That size, you want it to be approximately equal to the size of the set I such that xi equals 4, right? And that is, okay? That makes sense? All right, so now we've set it up. We have, let's say, one variable per pixel, maybe some side variables for properties of the different segments. We have constraints saying on each of these edges that nearby pixels want to have similar labels, and pixels should express the visual properties that their segments imply, right? So that would be our setup. Now, how do we go about solving it, right? So I'm not going to ask you guys that question because that's our job to teach you later in the course, but I wanted to mention a few different possibilities. So one thing that people will do for problems like this often is they'll write a relaxation. So they'll take the original hard optimization problem and try and replace it by an easier optimization problem, maybe one that has more solutions. And there are a bunch of different ways to relax this particular problem. I've seen lots of papers coming up with cool, clever ways to relax it. So there's linear program relaxations. There's a quadratic program relaxation. I've seen a second-order cone program relaxation. Turns out you can reduce it even to an eigenvalue problem. This is called the Cheeger relaxation. So there's a ton of different ways to approach this problem, and all of them wind up having different approximation properties. And then once you decide what approximation of the problem you're actually going to solve, then there's a ton of different algorithms that you can actually use to solve that relaxation, right? So there's a lot of choices there. And so even for just this, relatively well-specified problem, I think I've enumerated a space of, millions or billions of different algorithms that you could apply to it if you take the cross product of all of the choices that we came up with. So I just wanted to sort of try and impress on you how much the setup actually matters, right? And for the rest of the course, we're going to sort of, maybe assume that the setup has already happened, and tell you how to solve the problem once it's been set up. But I don't want you guys to let out of your mind that the setup is a place of a lot of flexibility, and you should be thinking about, okay, here's an algorithm that we're looking at. What does it imply about what was a good way to set up the problem? Right? All right, so I think that's about all I wanted to say about this this example. Are there more questions? All right. So, oh yeah, here are some edge detectors, right? This was an office that I once worked in, and that's the result of an edge detector. You can tell that the strongest edges are on the printout that I made to make strong edges to take a photo of, but there are definitely edges elsewhere in the scene. All right. So let's take a brief break right now, and when we come back, we'll start on gradient descent. Okay, so let's turn the mic back on. Here we go. Okay, let's get started again. So right, we're going to start talking now about actual algorithms. as opposed to all of the motivational stuff. So please stay motivated, but start thinking about algorithms. We're going to start with first-order algorithms, and the granddaddy of all of the first-order algorithms is gradient descent. So a lot of you have probably seen this before, but the algorithm, it just proceeds in a bunch of iterations. So we start with some arbitrary guess at x0, the thing that we're trying to find. So, and the goal here is we want to find, right, the min over x of f of x, right? And so we start with x0, and at every step of the algorithm, we just keep iterating. And at every step of the algorithm, we compute the gradient, right? This is the derivative with respect to x of f, right? Evaluated at x equals xk, right? And we add a multiple of the gradient, or in this case, I guess, subtract a multiple of the gradient from x, and that gives us our next x k plus 1. Right, or we add it to xk minus 1, we get xk. And so our choices here, right, it's a really simple algorithm, but we do have a few choices. We obviously can choose where to start. There's not much I can tell you about that other than start somewhere near the optimal solution. Right, nice advice if you can follow it. Starting at 0 is what a lot of people, use as a second best solution. We can choose the sequence of learning rates. So we could have it, for example, we could have tk be the same over all iterations k. We could have it be decreasing slowly. We have a choice about what rate is decreasing, what the initial value is, that sort of thing. And then finally, maybe a less obvious choice, we have to choose when to stop, right? We have to choose when we say, okay, we're good enough. We can come back to the user and say, here's your near optimal solution. All right? So here's an example of gradient descent. So here's a random function that I just coded up in MATLAB, right? So it's sort of got some two dips next to each other, right? And there's a contour plot at the bottom. So if you look at the contour plot, these contour lines, right? They're all along the contour line, the function takes the same value, right? And they're called level sets. I think Ryan already used that word. And then the sublevel set is like the filled area within a contour line. That's everything where the function is less than or equal to a particular value, right? And so you can see that some of these sublevel sets are sort of nice ellipse-ish shapes, and some of them are kind of weird figure 8 or peanut shapes, right? So if we, so here's the contour plot again, and if we start gradient descent, right? Let's say we start gradient descent right there, right? Well, so the gradient is going to wind up pointing in, well, I guess the gradient will wind up pointing in this direction, right? So it's going to be orthogonal to the contour line and pointing in the direction uphill, right? And so our next point, well, we'll go some distance in that direction. Let's say we go, over here, right? And then the gradient here, it's going to be orthogonal to those contour lines, right? So we go some distance. Let's say we go over here, right? And here's the gradient here, right? And so you can see maybe we go, over this far. Let's say we're right, and then I'm going to, I'm going to stop at this point, but you can sort of see what the algorithm is doing, right? Now, if we followed this particular sequence, right, we'd wind up right about here. So this is a good opportunity for me to use the phrase local optimum, right? Local optima are the bane of gradient descent. Right? A local optimum is a place where there's nowhere to go from here. The gradient is 0, and it's sort of increasing in all directions. But it's not the lowest that you could possibly go, right? Because over here, the colors are much darker, meaning that the function value is much lower, right? So if we had been smart or lucky enough to initialize gradient descent there, right, where the gradient is pointing maybe that way, right, I will bet that it will eventually get us to this global optimum right there by some path, right? And so that's the usual prescription for an arbitrary function, is that you just initialize in a lot of different places, and eventually you hope you get to the global optimum. Maybe something kind of interesting. What if I initialize gradient descent right there? Anybody got a thought about what's going to happen? What's that? Oscillating between both. Nope. Not unless we set the learning rate too high. I'll give you a hint. What's the gradient at that point? I hear 0 from everybody. So it's going to stay right there, right? So this is kind of an interesting one, right? Because if you look in this direction, right, the function is increasing in both directions. And if you look at this direction, the function is decreasing in both directions, right? So it looks kind of like this, right? It's called a saddle point because if you think of an old, Western style saddle, right, it sort of curves up and curves down at the same time. And so gradient descent can, in principle, stop at a local minimum, a global minimum, or a saddle point. There's the saddle point thing rarely happens. Why? You really have to be really lucky, right? So if I started, so here's the saddle point, right? If I started just a little bit away from it over here, I'd fall into this local optimum. If I started a little bit over here, I'd fall into this global one, right? And so it's sort of unstable, right? You're sort of balancing on, think of a marble balancing on top of a hill, right? If you're really, really good or really, really lucky, you can get it to stay put, but probably it rolls off in one direction or another. So one other thing which can happen to gradient descent, which isn't, I can't show it here because I have a finite slide projection screen, is that suppose that you had something that just went down like that, right? And so your gradient descent would keep going and going and going out the door, down the corridor, over into Wien Hall, right? And it would just keep on going out to infinity forever, right? And then the last thing that can happen to gradient descent is basically it happens if you set the learning rate too big. You can just bounce around sort of chaotically forever and not converge to anything, right? So we're hoping for the global optimum solution. Usually we're sort of okay with a local optimum solution. We don't worry about the saddle point, and we're okay with it sort of. I mean, we're decreasing the function value, right? So we want to know that we can keep decreasing the function value forever if we keep walking. And we sort of hope that we don't get the chaos answer. Okay. So, in machine learning and statistics, there's this nice situation for gradient descent and for all other optimization problems as well, that sort of bears paying special attention to, and that's this. We often have our function that we're trying to minimize. It's equal to the expectation over some distribution p, right? Of let's say p of I, right? So I is the thing being sampled, of fi of x, right? So the idea is that we sample a random element of our set according to this distribution p. We get a function that's associated with this random element. We evaluate that function at our point, and we take the expectation over all of the samples we could have possibly gotten, right? So here I is distributed according to p of I. And so an example of this is linear regression, right? So if we have some vector a in R2, some constant b in R, right? Or a scalar b in R, we could have, well, a dot x minus b squared, That could be our objective, and then we take the expectation over all possible choices of A and B, right? And that would be a linear regression problem. So what we typically do in a situation like this is this thing is really hard to evaluate because we have to integrate over a possibly infinite distribution, and we might not be able to do that. We might not even know P. We might just be able to sample from it. And so what we'll do is we'll let our index set, capital I, be an independent, identically distributed sample from P of I, right? And we'll make our approximation f hat of x equal to the sum over I in capital I of fi of x divided by the size of the index set I, right? So that's a sample approximation to the expectation. And so we'll often wind up with an objective function that looks like a sum of terms where each term is sampled from some distribution, right? And there could be a boatload of these terms, right? I've seen, like, imagine you're Google or Yahoo or somebody like that, and your sample set is the set of all web pages, right, out on the web. So they actually collect a decent fraction of all of those web pages, and they want to train models where their sample set is all of the web pages that they've spidered, which I don't even want to think about how many that is, but I also don't want to think about trying to write a program on my laptop that sums over all of them, right? All right. Yeah.
So the first one you said that you have fi of x, and you said that
Mm-hmm.
f can be different for every x that you sample?
F is different for every I, right? So the thing that's being sampled is I. Here x is the parameter, right? So it's like the weights in a regression. So for consistency with earlier notation, right, I is the sample and x is the parameter. Okay, so I told you about all of these, all of this flexibility that we have, and I want to talk a little bit about how we go about choosing. So I told you, start wherever you can. I don't have any good advice for you about that except problem-specific advice. But when do we stop, right? So it turns out the reason I mentioned this machine learning statistics case is that the answer is different there. There's actually a really good answer, and that answer is called held out data, right? So what will typically happen is we do something like we sample two samples, right? So instead of just one sample I, we'll sample I train, and we'll sample another one called I validate, right? And we'll use this one to make f hat train, and we'll use this one to make f hat validate, right? And what we'll do is we'll use f train to compute the gradients, right? And so as we do gradient descent, we'll get something that looks like this, right? So if we do iterations of gradient descent k, and if we do f of xk on this axis, right? So it'll start off high, and it'll just keep going down, and it'll keep going down, right? It'll look something like that. But then if we, and so this is, this one here is for f hat train, right? And if we do it on f hat validate, it'll typically look something like this. Right? So at some point, they'll start off going down one means going down the other, but they'll at some point they'll diverge, and where you want to stop is just here, right? So stop here, right? And you can do that because you actually know f hat validate, and it turns out that if you do that, then some other set that you sample, you're likely going to perform pretty well on. Whereas if you keep on going, you're likely going to overfit and won't do so well, right? And I won't talk about the statistical reasons for all of that, but this is actually a really, really good way to decide when to stop. And so I figured we should mention it, especially because this is ML and stats course on optimization. Now, there's sort of two ways to think about why it is that you want to do that. One of them is regularization, right? Meaning that performance is going to get worse if you keep going, so you might as well stop. And it turns out that this is actually a really good way to regularize. Like, people have tried to come up with explicit regularizers that are as good as this, and it's actually quite difficult, right? So this is an example where it's an algorithm that in many ways beats the optimization specification of the problem, right? It's really hard to explain why it is that early stopping on gradient descent is such a good statistical regularizer. The other is, well, I'll write it as why bother, right? And what I mean by that is, okay, we don't actually have access to the true f we're trying to optimize. Instead, we're optimizing on this f hat, either f hat train or f hat validate, or maybe we test in the end on some combination of the two of them. And so there's some error in that approximation. And let's say that error is on the order of 10 to the minus 2. We're accurate to 0.01, right? Well, there's not much point in keeping on with your gradient descent down to the 7th digit when the thing that you're optimizing is only right to within 2 digits, right? So that's a good reason to stop, and it can often result in very efficient algorithms. If you have some idea of sort of what the best possible accuracy could be, and don't bother trying to go beyond that, right? This is the old saw of measure with a micrometer, mark with chalk, and cut with an axe, right? There's no point in measuring with a micrometer if you're going to cut with an axe at the end. All right, so what's next? All right, so the next, in general, so even if you're not solving a machine learning or stats problem, you can do stopping based on convergence bounds, right? And these convergence bounds are usually, they usually look something like this. The accuracy in the end is going to be something like, right, our error epsilon is going to be less than or equal to, well, f of x0 minus f star, right? So here f star is inf x f of x, so it's the thing we're trying to find. So if we start far away, it'll take longer. Then we'll have some function of, this should be the number of iterations, k, has to be bigger than some function of 1 over the accuracy that we require, right? And then some constant that depends on the function, right? So usually we'll know what this function is. We'll know what the accuracy we require is, and we'll know what this functional form is in the bound. We won't know this, but we may be able to estimate it. For example, we'll tell you later how to use convex duality to get a lower bound on f star, and we can actually evaluate f of x0, right? So we can bound this thing. And then this constant that depends on f, we also don't know that, but we can often bound it using assumptions about the form of f. So for example, a limit on its gradient or Hessian or something like that, right? And so in order to get this to work, we need estimates of this term and that term, but we can often get those. And then we can say, well, if we've done this many iterations, then we're good, right? And so that's sort of one of the goals of doing the theoretical analysis, is to be able to know when to stop. And I think that's actually a good place for me to know when to stop, because it's 10 to 3. So we'll see you next time.